In this example, we're going to be looking at this structural member over here on the upper left-hand side of the screen. In particular, on the face, which is shown here, we're going to apply different loads. We're going to put an axial force, going to put a shear force in Y, a shear force in Z. We're going to put a bending moment about the Z-axis and a bending moment about Y. We're going to keep track of the state of stress at 2 points in the cross-section, point A and point B. A is shown here in the stress cube on the lower left-hand side. On the lower right-hand side is the state of stress on the cube. Up here on the upper right side, we're going to show the combined loading that's on there. So keep track of how this loading here influences the components of stress that we draw there for points A and B. First thing we're going to do is put a torque about the x-axis. So the component in this case is a shaft with its axis there of x. We can see here at point A with the right hand rule here that's showing the torque with the thumb pointing in the x direction. That's going to be putting a shear stress on A pointing to the left, and it's going to be in the Z direction. So on this space right here, it's pointing in Z. Of course, the shear stress is appearing in groups of 4. I'm showing only the front 2. Coming down here to point B, we see that the shear stress is down in the negative Y, and therefore that's why I draw it here. In each case, the shear stress on those faces is the torque times the maximum radius, big R, divided by the polar area moment there of J. Now let's say we put a bending moment about the Z-axis. With the bending moment about the Z-axis, we see that the lower fibers of that beam here is going to be in tension on the bottom, and it's going to be in compression there on the top. So as we see it here, it's going to be pointing in the positive X. So if we look here at point A, it's going to be in compression, and that's why I drew it as I did here. However, since B is on the neutral axis of that beam, you see no contribution to the normal stress there at point B. What if we now put a bending moment about the y-axis? In this case, our bending is such that along this line here, the beam is going to be in tension, this side in compression. It turns out for this bending moment, A is on the neutral axis, so there is no contribution to the normal stress shown there at A. At B, on the other hand, we see that since that's in tension, we draw in the sigma x here, which is the my over I generic term. In this case, the y variable here is r. So again, keep track here of what's going on this face where we already have a torque and 2 bending moments, and it's given us dramatically different or significantly different results in terms of stress. Now let's put an axial force on there. The axial force Nx going on here, that puts a uniform normal stress on the face. So for both A and B, I'm adding on Nx over A. If I put a shear force in Z, well, the shear force on Z, we know with the equations we have derived for the bending beams with a shear force, we know that the maximum shear force is going to appear on the neutral axis for that kind of loading. So that says here at A, we're going to get a shear stress, which is 4/3 Vz over A, which is shown here. For B, it's on the outer surface, and therefore there is no shear stress here, because on the outer surface here at both B and then on the back side over here, the shear stress is a 0. So you're going to see a contribution on this point A, but nothing there on B. Whereas if I now put a shear force in the y direction, it's just the opposite. The maximum shear stress is occurring on that axis, which is Z. So I'm going to be putting on the 4/3 Vy over A like this. But being as that A is on the outer fibers here of the beam in the direction of the shear stress, of the applied shear force, then there's no contribution there. So over here on the right face, again, we have all possibilities now. We have all three components of force, Nx, Vy, and Vz. We have all components of moments acting at that point, Tz, My, and Mz. And at point A, here is our combined state of stress. We have nothing for tau xy, but we have two contributions to the normal. That's from the bending moment Mz, the normal force Nx. For tau xz, we have a contribution to the torque and to the shear force there of Vz. On B, it's a different case. We still have the normal stress equal to Nx over A, but in this case, it's the bending moment My that makes a contribution to the normal stress. The torque puts its shear stress in the negative y direction of Tr over J, and the shear force Vy puts a shear stress at B in the positive y there of 4 Vy over 3A. So carefully if you need to, go back and review this step by step. But in the end, we see that this complicated loading at the cross section gives us quite different results for A and B, but they're all based on very fundamental ideas that we've gone through this semester.